So welcome back. In this video we're going to quickly have a look at the visualization of complex numbers and all the associated measurements. So what we do basically is called the complex plane. You do remember that a complex number, Z, is composed of two parts. The real part, alpha, and the imaginary part, beta. So you can basically regard a complex number as a vector of those two components, real part, imaginary part. And that's just how you can visualize them. You can visualize them as points or vectors in two-dimensional plane. So instead of just a line, as for R, we now need two axes, one for the reals, one for the complex part. All right, so complex numbers correspond to vectors in a two-dimensional plane with a real axis and an imaginary axis. And that's just what we do here. Let's have a quick drawing here. So I need two axes here. One is called the real axis. Oops, sorry. So that's this one, the real axis, and one is called the imaginary axis. So here we have the numbers 1, 2, 3, and so on. And of course, -1, -2, and so on. And on the imaginary axis, we have the numbers I, 2i, 3i, or -i, -2i, and so on. Now, let's just take an arbitrary real number, complex number. As an example, we'll use the number 3 plus 2i. And that corresponds to the point 3 units to the right, 2 units along the imaginary axis. So this here is the point that corresponds to Z in the complex plane. Or you could also use the vector that points to this point here. So that's a visualization of that complex number. You can easily see the absolute value of that vector. That is precisely how long that vector is. So this here, this length here, that's the absolute value of Z. You can also visualize the negative complex number and the conjugate complex number. The negative complex number, that's just -3 minus 2i. So that one is here. So that is minus Z. And you get the conjugate by just mirroring along the x-axis, along the real axis. So that has the same real part, but negative imaginary part. So here that is Z bar. Okay, that's the complex conjugate of Z, 3 minus 2i. And I'd just like to mention one more thing in connection with this visualization. We have a vector here in the two-dimensional plane, so we could also associate an angle to that vector, and that's the angle between the vector and the real line. This vector here, this angle here, sorry, that also has a name that is often called the argument of the complex number set, just to show that you further. Okay. Now there's one more formula I'd like you to know about complex numbers. I won't talk about the derivation or the proof of that formula too much. It's enough if you know that, because we need that for differential equations in just a few videos. And that is the very famous Eulers formula. Eulers formula, just state that. That's a formula for expressions of the form e to one complex number. Right? We haven't talked about the complex exponential function. It can be defined in a similar way as the real exponential function. And of course it behaves the same on the real numbers. On the complex, on the imaginary numbers, what it basically does is it rotates. So e to something imaginary corresponds to a rotation, and that is what is expressed in Euler's formula. This exponential function can be written as the cosine of beta plus I times the sine of beta. Now that's basically what you have to know about the complex exponential function. There's one nice consequence of that one. And you get that if you use beta equals pi. So what happens if we use beta equals pi? Well, what that formula tells us is e to the I pi is then the same thing as the cosine of pi plus I times the sine of pi. And of course we know what cosine and sine of pi are, right? So the cosine of pi is -1 and the sine of pi is 0, so that is -1. Okay, and again that's a celebrated formula in mathematics, a very, very famous one that states e to the I pi plus 1 is 0. So here we have a connection between the most fundamental numbers in mathematics. There's Euler's number e, there's the imaginary unit I, there is pi, and there's 1, and there's 0. So that's basically the most important, the most fundamental numbers in all of mathematics. And here's a connection, a deep connection between them. And this formula is often named the most beautiful theorem in mathematics ever. Okay, that basically concludes that section about visualization. I just wanted to give you a very brief introduction into how to visualize complex numbers and into dealing with the complex exponential function, especially Euler's formula, because we'll make use of that when we finally get to solving our systems of differential equations in a bit. Okay, see you then. Have a nice day.